All right, let's get started for today. We're going to switch gears, and we'll look at something called adversarial search. So let's start with a kind of review of game playing and AI. Kind of one of the oldest games people started looking at just when they started doing AI is the game of checkers. Because back in the 1950s, they had computers that could do less than our calculators today. So they programmed them to play checkers. It wasn't good at the time, but by '94, we actually had an AI world champion for checkers. And this was by beating the then 40-year-long standing world champion in checkers, who just nobody else could beat. He all of a sudden got beaten by this AI system. Since then, we've gotten even further with checkers. So we got to the level of the best human in '94. In 2007, we got it fully solved. What does that mean? It means that the computer knows exactly for every possible scenario what to do to make itself win or to get a draw, whatever is the optimal thing to do by thinking ahead through the entire game all the way till the end. Just like you could think ahead for a simple game of tic-tac-toe and ahead of time know that it's going to be a draw, computer can do that for checkers. It knows ahead of time what it's going to be, unless somebody makes a stupid mistake, and then you can take advantage, of course. That's what it means for a game to be solved. The earlier player, the '94 player, didn't fully solve the game. That player did things quite similar to what we'll cover in lecture today, with, in addition, when there's only 8 pieces left on the board, a special endgame database that very quickly looks up and essentially has the solution stored for when there's only 8 pieces left. More difficult game, chess. So in '97, we had the match between Kasparov and Deep Blue, and the second year when they played their matches, Deep Blue actually won. So at that point, computer chess players reached the level of human expert chess players. They do it very differently than human players. They explore a lot of possible scenarios, a lot more than humans could. But the bottom line is that they come out with a really good play of playing chess and are at the expert or even above the best expert level now. The methods underneath Deep Blue, we don't know for sure exactly what was in there because it wasn't fully published. It wasn't an academic endeavor. It was a company, IBM. So it's not 100% clear what happened, but the basic things they did are very similar to what we cover in lecture, with for sure a lot of special tweaks and optimizations and a really good evaluation function for board situations. Then the next game on the horizon was Go, and at the time, computer beat Kasparov in chess. Go was still not at all within reach of computers. With Go, the problem is that at any given time, it's possible that you can choose between 300 different moves. So that's a branching factor of 300. There's a lot of pieces to be placed on the board. So this is a huge, huge game tree. The same techniques that worked for checkers and for chess didn't end up working out for Go because of this huge branching factor and because of the fact that you need to look pretty deep into the game to understand the relevance of your current moves. Now, recently, people have come up with something a little different called Monte Carlo evaluations of a game situation, where they actually simulate stochastically what might happen from a certain situation on. And that's allowed them to make quite a bit of progress. And now it's actually become reasonable to try to see if a computer, does something reasonable against a human player. Back in the '90s, humans wouldn't even play against computers, so it was just a waste of their time. Now it actually can challenge some of the better players. Then, lastly, what you want to know for your project 2, how about Pacman? Nobody's really pushed Pacman all the way yet, as far as we know, but your project 2 is your chance. So let's take a look at kind of what we're after here. We've seen in the first 2 kind of technical lectures how to search for one agent. The next 2 lectures we looked at constraint satisfaction problems. Now we're back to the agent that we initially cared about, Pacman, but there are also ghosts in the picture. So we have ghosts that are playing against us. What we're after is behavior that maybe looks like this. And when you watch this, think about what kind of computation might go underneath making something like this happen. All right, this is really good. In the very beginning, when we talked about Pacman and search, we said one type of agents is just these reflex agents. A reflex agent is one where you just code up, straight up, a couple of rules and say, if a ghost is nearby, run away. If a power pellet is nearby, run to it. But then if there's a ghost and a power pellet nearby and they're in the same direction, you might not know what to do, and you need to kind of refine your rule and say if the power pellet is close enough that you'll reach it before the ghost reaches it, then run to it, and so forth. And so it gets very complicated to code something up like that. And we saw something much better, which was search. And we could find solutions to a lot of single-agent search problems quite efficiently with things like A-star search. Today we'll go extend essentially A-star search. So in the sense that we'll again come up with a formulation. Something where we say this is a game. Like we used to say this is a search problem, now it'll be this is a game. And we'll have solution methods for those games. So all we'll have to do at the end is specify the game, and then the method will solve it for us. Just like in A-star, where we had heuristics to make things go fast, here we'll also have some things that will come up to make things go faster. Okay, so the main thing we'll look at today is adversarial games. What do we mean with that? It's games where you fight over the outcome of the game. You play against another person, right? So what other games are there? Well, to break down what kind of games there are deterministic games, where the outcome of an action is always known ahead of time, or stochastic games. Stochastic games such as, let's say, backgammon, where the roll of the dice is stochastic. You don't know what's going to happen. Poker, you don't know what cards the other players have. We're not considering those for now. It could be one player. We've already seen that. It could be two or more. The special property of games, whether they are zero-sum or not. Consider a two-player game. And at the end of the game, when the game's over, the two players each get a payoff. A simple scenario is one where the winner gets a payoff of 1, the loser gets a payoff of -1, and it sums to 0. There could be other scenarios where maybe the winner gets a payoff of 5 and the loser gets a payoff of 4. And you can have any kind of payoffs at the end of the game. You can define those. That's what defines what you try to get as the outcome of your game. For the special case where it sums to 0, you actually only need to define one number. And one player gets the positive version, the other player gets the negative version. And so those are the zero-sum games, and that's where you will play against each other. You're guaranteed to be pitched against each other because you get the opposite outcome of the other player. Those are the ones we're going to look at today. Checkers falls in that category, chess, Go. Most of the kind of two-player games that you know of will fall in that category. And there's something else that distinguishes games, whether there's a fog of war or not. Do you know what's happening, or do you not know what's happening in the game? Let's say you play StarCraft. You might not know until you go scouting what's happening in other parts of the StarCraft world. So there's a whole other concept there of going out and collecting information. Today, we're not worried about the information collection and things that are unknown. We assume we know the entire state of the system. In this situation, because there is multiple players, the solution will not just be a sequence of actions. For project 1, the solution is always a sequence of actions. For this here, it's not the case, because you don't know what the other player is going to do. So the solution is a policy or a strategy which encodes for no matter what situation you encounter in the future, here's the action I will prescribe. So deterministic games is what we'll look at. There's a start state, a set of states in general that we could be visiting. There are players, 1 through n. Today, mostly 2, but sometimes 3. We'll have 2 ghosts sometimes. Actions, and they can depend on the player type and on the state. There's a transition model. This is the successive function from lectures 2 and 3. There's a terminal test. That's a lot like a goal test, but there's something different now. There's not just a goal test, but then there's something called terminal utilities. And they say, for a given terminal state, how desirable it is. So they attach a number for each player, how desirable that outcome is as the terminal state for each of the players. And then the solution is something for each player, prescribing what we call a policy, which is an action for each possible state that you could be in. We'll mostly look at zero-sum games. As I said, those are the ones where the two players have the opposite desires. So you can characterize the utility values at the very end here with just one number. The maximizer player will try to maximize that number. The minimizer player, who effectively gets the negative of that number, will try to maximize the negative of that number, so it's trying to minimize the number we specify. This is what it looks like. You fight over one thing, and whoever gets it wins. Who doesn't get it loses. There are more general games. There are games where the utilities are not just one number. And it could be that, for example, blue robot looks for green gems, and red robot looks for orange gems. And in this case, their utility functions are not adversarial, and they might even collaborate, because it might be because of the red robot picking out the red gems, the stack gets smaller, and the blue robot has less work finding the green ones. So depending on how you define your utilities, you can have collaborative behavior emerging or adversarial behavior emerging, or yet something in between. Okay, so how does this work, this adversarial scenario? You're the first one deciding on your move. You're the maximizer blue robot. What are you supposed to do? Well, you have a bunch of actions available. Now, you ought to do is you ought to think, if I take a certain action, what will the other player do? Because that will determine what's the right thing for me to do right now. The other player will go through the same process and will be thinking about, am I in this particular situation, and I take an action in the resulting state, what will the maximizer player then do, and so forth. So you get this recursive chain of thinking about what the other player would do in this next situation, and that's what allows you to evaluate how good a certain action is. So let's try to formalize this, and we'll start with just one agent. So this Pacman, no ghosts yet. This is our initial state. There are two actions available, left or right. Then after that, some more actions available. And what we do now is we somehow work our way all the way to the bottom of the tree. I know we've seen algorithms in lecture 2 and 3 to not draw the entire tree to start out with. We'll do the same thing here. But for now, let's look at the entire tree. And at the bottom of the tree, there are utilities for every possible outcome. If you're the only agent, what you do, well, you get to control everything. So all you need to do is to look at the bottom here, at all these utilities. And turns out 8 is the highest one. And so your optimal strategy is to say, I'm going to move to the right, move to the right again, and I'll get a utility of 8. Another way to think of this is, and let's look at this at the next slide, is that every state has a value associated with it. What I mean with a value is that for every state, there's this number, one number, and it encodes the best achievable utility starting from that state. Assuming you did all the right things from then onwards, what would be the utility you're going to achieve? For the bottom nodes, that's very easy. You can just read them off because there's nothing left in the game. For higher up nodes, the way you can find those utilities, the values, is by propagating things up. If you're wondering, what is the value of this state over here? Well, for that state, you could go here or here. Now, who went here? What's the value here? Let's say these are all the numbers, then the value here is 6. Best of all possible outcomes underneath here. Then for this state, the best possible outcome would be 8. So the value of this state here would be 8. Similarly, we can work on the other side through the tree. 2 and 0 are the best, so it's 2. 2 and 6 is what you have, so 6. The best here is 6. And now the best among all options for the top node is 8, and that's the value of the top node in this tree. So this is a bottom-up process. Yes? Which one is the same as the start state? This one here? Okay, that means something funny is going on in how we arbitrarily assign these numbers at the bottom there. Good observation. So terminal states, we know the values. Other ones, we just take the max, and we can propagate things up. Fairly straightforward. What now if there is a ghost? Adversarial game trees. Well, let's say Pacman still gets to move first. These are the two possible next states. But after that, the ghost gets to move. This is our tree expansion. And let's say the game stops after one move by Pacman, one move by the ghost. So it's a very short game. Each player gets one move. And these are the terminal states. These are the terminal states. And we assign values to them. The values of these states are, in this case, +8, -10, -5, -8. Let's not worry about where they came from. They come from the person who defines the game for you for now. What we're interested in is propagating these values up. If we had one agent, it was very simple. We could just look at the highest value, which is +8. We said, that's the best outcome, and let's find a path to the +8, and we're done. Now Pacman doesn't get to decide how the game will go on its own. Pacman just gets to decide the first move. And if Pacman would decide in the first move to go over here, actually the ghost would decide to go here, because the ghost is trying to minimize the number at the bottom. And so you would not get +8. You would get a -10. So what you see here is that the value of this node over here, because the ghost gets to play, is the minimum of the values underneath. And same thing over here. The minimum of the two values over here is -5. And then at the top, Pacman does get to play. You pick between -10 and -5. -5 is better. And so you would go left. Oh, you're right. -8. -8 is best between -8 and -10. And you would go left. So it's a very different process where in each layer, it depends on which player is playing, how you propagate the numbers up. What we just computed here is what is called the Minimax Values. So the terminal states are known in terms of Minimax Values, and then for every higher up state, you either apply a min operation or you apply a max operation depending on who is playing. We can do the same thing for a bigger game, like Tic-Tac-Toe. You could draw out the entire game tree. It's actually possible for Tic-Tac-Toe. It's not too bad. Found not on the slide, but on something bigger. If you were to do this, at the very bottom of the game tree, every number would be either a -1 if you lose, 0 if you have a draw, 0 if you have a draw, +1 if you win. There will be no other numbers the way we define the game. If you think winning is what you need to do, losing is worse, and draw is in between. From what we just saw, the way we compute the Minimax values, the value of every state anywhere in the tree will then also be either -1, 0, or 1. It's impossible to find other values, because the only way these values can come about is by being propagated up, and we start with just these three values. Now, if you ever thought about this, many of you might have, you think about Tic-Tac-Toe, what is the value of the game of Tic-Tac-Toe at the very top? What are you going to find here? 0. Why is that? Because if the other player plays really well, plays the right way against you, there is no way you can do better than forcing a draw. Now, of course, if they make a mistake somewhere, you might do better. And there are nodes somewhere in the tree. For example, down here, there's a node that has a +1. And right above it, there will be a node that might have a +1 and so forth. But all the way at the top, 0 is the number that you find because that's the best you can do. That's what I meant in the beginning of the lecture when I said checkers is solved. For checkers, somebody figured out the number at the top of the tree by computing the whole thing. And that means against that kind of player, you just stand no chance. If they always consequently execute the optimal move, you'll just have whatever the initial outcome is. If they say, you want to play checkers in against the computer, you'll never win, right? It knows what to do. Same for Tic-Tac-Toe. Okay, so we saw our first algorithm, our kind of baseline algorithm that we'll be working with. You can, in principle, solve games like Tic-Tac-Toe, chess, checkers, and so forth. The algorithm we looked at is called Minimax Search. We look at this tree over here. What would happen? You would have the 2 over here, the 5 over here, and then the 5 as the Minimax value of the tree. the policy you would find would be that max would go here, min would go here, but also if max were to make a mistake, min also has something it knows it would do, and it would go here if max were to make a mistake. If we compute this minimax value at the top and the associated move, we know what to do at the top, and then we can either repeat this process or we can just have stored what would happen. If everybody plays optimally, we know ahead of time how it'll play out. It's possible the other player does something suboptimal, in which case you want to recompute for the new state exactly the same thing and see what's optimal now. In terms of code, very few lines of code. There's a max value and a min value you need to write. How do you write it? You initialize the max value to be minus infinity. Then you loop over all children of that node, and you do a recursive call. For the children, you call the min value function. This will return the value of that child, and then you compare it with the value you already had. If it's better, then your max value has improved for that particular node. Once you cycle through all the children, you know what the max is, and that's what you return. The minimizer has the same thing, just symmetrically done. Now, to make this work in practice, you'll have to have a little bit of kind of wrapper code around it. And one way to think about it is that there is this overall dispatch function where you compute the value of a state. Then when you're asked to compute the value of a state, you check. If the next state, the current state you're looking at, is a terminal state, they actually just return the utility of that terminal state. That's the base case. If it's a maximizer node, you call the max value function. If it's a minimizer node, you call the min value function. And these are the same functions we already looked at. So this is your pseudocode for project 2, problem 2. Okay. Let's do an example and see how this code runs. On paper, when you solve these problems, it's convenient to start bottom up. I just want to illustrate how this works when a computer runs this. A computer doesn't lay out the entire tree and then starts from the bottom and works their way up. Computer will run this as a depth-first search, right? It goes down to the first child. For the first child, it checks, is it a terminal node? No. Then recurses, right? Gives the values of all the children of that one. Here it's a terminal node, so no further recursion. 3. So right now it says best value is 3. It sees 12. Well, 3 is still the best. For the minimizer, 8, 3 is still the best. Passes 3 back up. Then the depth first search goes down the next branch. Here, it's a minimizer node, so it has to, again, look at its children. First one is 2, so that's what we have. Next one is 4, worse for the minimizer. 6, also worse. So 2 is being passed up. This node here at the top, at this point, had a 3. Gets the 2. 2 is worse for the maximizer, so nothing changes. Then it goes to its next child. Next child, minimizer. You have to look at all its children. 14 is the first number. Next one, 5. That's actually better for the minimizer. Then 2, that's even better. The 2 gets passed back up because it's the last child. Then this node here compares that with the current value, which is 3. 3 is better, so it finds 3, and that's it. And it somehow needs to store where that came from. Otherwise, you will not know which move to make. So in your code, you'll need to do a little bit of bookkeeping, so you do know that 3 came from the first action. Yes? We're minimizing on the last level. We're minimizing here because we assume that this is a maximizer player, and this is a minimizer player. And the way we denote them pictorially is a maximizer is an upward pointing triangle, and a minimizer is a downward pointing triangle. So it's just a definition of the game. You just as well have defined another game where they're both maximizing. That's not what we're doing right here. All right, so that's Minimax. How efficient is that? Well, it's a depth-first search. We know depth-first searches are very memory efficient. No worries there, right? Space complexity, branching factor, times the depth that we have to search. If we have a certain depth of the game, we know the game is at most, let's say, M deep. The way we run this search, we never quit early, right? In earlier algorithms where we looked at A-star search, we tried to find a goal. Once we found the goal, we would be done. Here, that's not true. Here we have to search the entire tree to find out what the value of the tree is. So we traverse the entire tree, and even in the best case, we're seeing the entire tree, and we have a time complexity that's pretty bad, b to the m. So exponential in the depth of the game. The longer the game can take, the worse, and the bigger the branching factor, also the worse. How about chess? Branching factor is estimated to be about 35 on average. The depth, 100, is a reasonable kind of average depth for a chess game. Okay? That would mean we're stuck with 35 to the 100, which is just completely infeasible. This is not what Deep Blue was doing. That's not feasible. So what we're going to do for the remainder of the lecture is kind of wrap our head around how we can avoid seeing the entire tree and maybe still do something useful. Before we do that, let's look at a couple of properties of how Minimax behaves. We've seen this algorithm. We've seen the definition of the game. Let's investigate whether it's something we're actually happy with. Is this something that we like as a solution, assuming we can run it? Here's a simple example. Two-player game, maximizer and a minimizer. Let's take 10 seconds for you all to think about what the minimax value of the game is going to be. What's the minimax value? I hear a lot of 10. Why 10? Well, the value here is 10. Here it's 9. And so up here it's 10. Is that the right thing to do? If this is the game you're solving, if you're asked to find the minimax value of the game, obviously then 10 is the right answer. But let's say you're solving a real-world problem. Is this going to be the right thing for your real-world problem? It depends, that's right. Maybe you're playing against a very mechanical player who's really good. They're never going to make a mistake. You know it. They're not going to maybe make the right move at the bottom and go to 100. You just have to do the minimax thing to get the best possible outcome. But maybe you look across the table, you look at your opponent, and your opponent looks like this. At that point, you might say, well, that guy doesn't look too smart. Maybe they're going to choose the 100 outcome. And you might be willing to take your chances. That's not minimax optimal play, but it could be optimal in a real-world scenario. This is something I want to point out now. We're going to look at that next lecture. How do we handle when you play against someone who might do something stupid every now and then, something random? But for now, minimax, keep in mind, doesn't really account for that. So let's look at a demo of how this can be detrimental at times. We're going to a Pacman scenario. Okay, what's going on here? Very bad situation for Pacman. Right? What happened? Let's watch this again. Let's pause it here. Okay, what's going on? Pacman's in between two ghosts. The way the utilities work is that at the end of the game, per move you made, that was a cost of 1. So if you made 5 moves, that contributes a -5 to your utility at the end. If you eat a food pellet, you get +10. If you win the game, you get +500. So the ideal outcome here somehow for Pacman would be to eat all these food pellets, which would be 40. The minimal number of moves for that would be 8. So that would be 32 points, right? And then winning the game, 500, so 532. Something like that. That would be the ideal outcome. But the ghosts are playing against Pacman. And the ghosts are in a really good situation right now. And they're just going to grab him, right? Now, Pacman runs Minimax and says, there's many outcomes. For any of the outcomes where the ghosts are really doing the right thing, they'll close me in and get me. The longer this game lasts, the more often I get a -1. So the optimal thing to do here is to just suicide into the ghost. And that's what we're seeing. Minimax in its full glory. Now the real question is, that's Minimax, right? And we'll see more of this next lecture, but this was Minimax. Now, let's look at the same scenario again. And now let's be a little more optimistic. Let's say, look at these ghosts. These ghosts don't look too smart. Maybe I should use a different solution method, which we'll cover next lecture, where I assume that the ghost might actually maybe go the other way. The blue ghost might run away from me, might be scared of me for some reason. And if that's the case, I can just follow it and eat all the food pellets, right? Specifically what we're looking at here is what would happen if Pacman, instead of doing a minimax thing, would assume that half the time ghosts will go one way, half the time the other way. And do the optimal thing in case half the time they go one way, half the time the other way. If they go towards, the blue one goes towards him, sure, nothing can be done. Half the time, this happens. Blue is going away, and you actually end up victorious. 532. So this is something to keep in mind while we look at Minimax, what the assumptions are. Because really we always have a real-world problem that we model as a Minimax problem, and you need to know whether it's the right fit for the problem you're really trying to solve. Here's something else that's really interesting about Minimax. You can actually get some cooperative behavior out of it. So far we've talked about minimizer, maximizer, Pacman Ghosts working against each other. Now, let's look at this game tree here. In this game tree, there are 3 players. There's a min 2, a min 1, and a max. What we're going to assume here is that these are actually 3 different players. So when the maximizer thinks about its move, it's thinking, if I make a move, well, what will min 1 do after that, and what will min 2 do after that? When min 1 makes the move, min 1 has to think, well, after my move, min 2 still gets to play. I have to account for what they will do. Now, if we do that, what does that mean in terms of values that we can propagate? Well, here for the minimizer, 1006, that's 6. Here, 10 and 8, that's 8. 102, that's 2. 20 and 4, that's 4. Then what happens in the next layer, this is a different player. It's a different ghost. This different ghost is saying, well, let's see what the values are below me, 6 and 8. I'm a minimizer, so I'm going to go for 6. And over here, I'm going to go for 2. And then the maximizer goes for 6. So what you see emerging here is that even though each of these minimizers can think of their own, they can just think of, I'm solving this Minimax game on my own. They don't need to communicate. They don't need to communicate about what they're going to do. They'll automatically do the right thing together because they know both of them are going to try to minimize the outcome, and so you automatically get cooperative behavior out of this. At least between the minimizers among themselves and the maximizers among themselves. Let's take a look at how that can work. We'll look at here is 2 ghosts and Pacman. Okay? What's going on underneath? Each ghost is running its own Minimax algorithm. It's not one global algorithm. Each one of them runs their own algorithm, their own Minimax. But you'll see, despite that they're running their own Minimax, on their own computers, so to say, they'll collaborate to make things work. So let's take a look at what happens. Pacman off to a decent start. But then they flank around and get him. Right? Let's watch that again. Okay, so this is really beautiful that despite the fact that these are separate agents, just because they happen to have the same utility, they'll end up cooperating on this problem. This will be true no matter how many minimizer and maximizer agents you have. All the minimizers will collaborate, all the maximizers will collaborate. Yes? Yes, it matters. So it'll affect what they do. So if you get, depends on the rules of the game, of course, but in these kind of games, we assume they move one at a time. And since they move one at a time, you have to build up your game tree in the same order as they will move in the game. Okay, let's take a break here. And after the break, let's look at how we can deal with these really deep trees. So one question came up during the break about Project 1. And essentially what came up is getting the extra credit is really hard, getting below those numbers. Yes, it is. It is really hard. So it used to be, including last semester, that instead of giving you extra credit based on what score you attained, it was the top 3 in the class. So only the top 3 would get extra credit, and it would be just the ranked thing, top 3 get extra credit. We thought that we'd change it up because you never know when you're in the top 3 while you're working on it. So if we give an actual cutoff number, when you reach that number, you know you're done, and you have your extra credit if that's what you want to get, right? And you don't have to worry about, maybe I should work another night because maybe somebody else is getting even a better score, right? But we did set the cutoffs based on the top 3 last semester. So don't sweat it if you don't make it there. Last semester, 6 people out of 330 made it there, okay? This is hard. This is for people who really want to challenge themselves and are just done with everything and like, I want to challenge myself, right? You're not expected to necessarily earn that extra credit. Okay. So let's restart. Resource limits. Let's say you're trying to solve a problem, and your agent is kind of trying to work down this tree, such a deep tree. Ideally, you look as far ahead as possible. That allows you to predict what would happen, but you only have so many computational cycles available. So that's not going to happen. You're not going to be able to look till the end of the game for a game like chess, unless you're very far into the game already. So pictorially, what that looks like is we have a tree that looks like this. Now, that tree is very deep. We cannot find the values at the leaves. There will be some values at the leaves. They exist. But we're not going to find out what they are in our search. So keep in mind, they exist. It's not that we don't think they exist. We just don't know how to get all the way to the bottom. Not enough time. So instead of searching all the way to the bottom, we might say, let's just search till up here. Assume the game only takes 2 steps. Maximizer makes a move, minimizer makes a move. And then we don't know what the utilities are there. They're not defined. But we'll define something ourselves. We'll define something that we'll use instead of the real utilities and put it in there. So -1, -2, 4, 9. Ideally, these numbers reflect what would be the minimax value right there. But that's really hard to get right. To really get that right, you would need to do the search. So it'll just be a number that you hope reflects as well as possible the minimax value of that particular state. So once you do that, you can propagate things up and compute the minimax value based on these kind of replacement utilities that you put in. These replacement utilities here, we call those, the way we obtain them is by using something called an evaluation function. And just like with A* search, you could have expensive evaluation functions. You had expensive and cheap heuristics. Expensive heuristics might give you more information, but you can do less computation because they're taking all your computational cycles, right? So there's a trade-off here too. You could have a very, very fancy evaluation function, and that might be more accurate, but then you have no cycles left to go down in your tree. Maybe you're stuck with just depth 2. If you have a simpler evaluation function, maybe you can work down till depth 10 or something. But then whatever you compute there might not be as accurate. So there will be a trade-off here, and you need to kind of find the right trade-off to play as well as possible. So suppose you have 100 seconds to compute, 10,000 nodes per second. That means you can check 1,000,000 nodes per move. That means you can, with something we'll see a little later that speeds up Minimax a little extra, something called alpha beta, you can go up to a depth 8. Still not super deep, but up to depth 8. And so if your evaluation function at depth 8 is reasonably good at evaluating what the game situation is like after 8 moves, then you might have a good player based on this. Optimality guarantees are gone. Keep that in mind. Once you start using evaluation functions instead of the actual utilities, no optimality guarantees. Searching deeper makes a big difference. And if you don't know how long it's going to take to search up to a certain depth, you could do iterative deepening. Just a second. So if you don't know how long it's going to take to search up to depth 8, and maybe you'll run out of time, maybe not, you can decide to just search up to depth 4. If you still have time left, you search again now up to depth 5, then 6, then 7, then 8. Whenever you run out of time, you take what you found from the previous depth, and that's what you will work with. Just like in the original search algorithms that we saw, you look at the search tree, it grows very quickly. So iterative deepening, the main cost will be the bottom layer anyway, so you don't lose a whole lot of time by doing 1, 2, 3, 4, 5, 6, 7, 8 compared to just depth 8. So that's a good idea if you play against the clock. Question there. Okay, that's a good question. How do you know what's a good depth? It's very tricky. The deeper, the better, typically. It's rare that less deep is going to give you a better result. The only reason less deep could give you a better result is if you have a bad evaluation function that happens to be, better somewhere and then worse when you go deeper. But for a normal evaluation function that has good accuracy, equal accuracy, and no matter how deep you are, deeper will be better. Now, there's a lot of optimizations people do. And we're not going to look at those. But let's say if you look at a chess playing computer, you go up to a certain depth. But let's say at that depth, you just captured the other player's queen. That's a big deal. You're in a good position. You just grabbed the queen. Let's say you used your queen to do that. In the next move, they're just going to grab your queen, and it's going to be equal again. Right? That's a problem, because now you think, oh, this is so good. But because you don't look deep enough to see your last move and not the next move that's going to happen. So what some people do in these algorithms is they'll look at the evaluation function as you go deeper and deeper, and they will not stop unless it's quieted down. So the evaluation function for consecutive depths is about equal, meaning that there's not something really funny happening based on your last move that maybe will be compensated for in the next move and then again in the next move and so forth. So that's a heuristic or a rule of thumb people use to decide where you're willing to stop searching. Yes? Okay, so that's a very similar question. So where do you stop? The simplest thing is to say, I only have so many computational cycles. I'm going to fix my depth. And up to a certain depth, and that's it. And at that depth, you call the evaluation function. So when you do your minimax calls, you will pass along as an extra argument how deep you are already in your search tree. And then the first thing you'll check is, if my depth is the final depth I'm willing to consider, then use my evaluation function. So that will be the first line in your dispatch function now. Something more complicated would be iterative deepening, because then you can adapt the depth to the amount of computational cycles that you have available. And something more complicated even would be something where you wouldn't stop unless the values given in consecutive depths are very similar, such that you don't have a weird thing happening just past the horizon. Okay, so that's what we can do to resolve the problem. Keep in mind, depth matters. The faster your code is, the deeper you can search, the better you're going to do. Right? Look at this example over here. Your robot's going on a hike, trying to get somewhere. It's looking ahead, it's kind of foggy, and could be a big monster here that's going to eat the robot. Or when the robot actually looks further, realizes just some trees and some hills. This picture here is what you have. You haven't looked deep enough. You're not far enough. You have a very fuzzy way of looking at what's going to happen. And the evaluation function does the best it can. It says maybe pretty dangerous, maybe not, right? Whereas here, your evaluation function would be very good. Be able to say very precisely what's ahead. The idea is that the deeper you can look, the better. Let's look at some examples for this. So what we'll look at here is Pacman in action with different depths. So let's pause this for a second. Again, not the best scenario for Pacman. What's going on here? One dot at the bottom. Again, a dot gives you 10 points. Keeping alive is -1. And 500 for winning the game. First, we'll do a limited depth search. Depth 2 search. So Pacman looks 2 steps ahead, moves based on that. Let's see what happens. So that's important here. After Pacman makes the move, the ghosts will each make their move. Then after they've made their move, Pacman will rerun a search, depth 2. Based on that, decide what to do, and this process will repeat. So Pacman doesn't just search once at the beginning, as you had in A* and so forth, but every time before taking an action, you rerun your Minimax search up to a certain depth. So let's see what happens. Okay, Pacman's thinking, depth 2. Now, here's a bad situation, of course. Pacman is going off to the left. The ghosts are all around it. And that's it. Not good. You might think this is just impossible for Pacman. It's actually not. Let's look at a depth all the way till the end of the game. Search and see what happens. They're running full depth. First moves up. Why is that good? Well, you'll see. Moving up was actually the right thing to do if you fully understand how this game is going to play out. Okay, after moving up, down. At this point, the ghost has made its decision, the blue ghost. The ghost always can kind of keep going the direction they're going, right? And so you actually win the game. There's a difference between looking ahead just a little bit and looking ahead far enough. Yes? It's pretty subjective. Some people use it for one thing, some people for the other thing. The term that's usually used is ply, and sometimes ply means one player playing, sometimes it means each player playing once. Okay, so we have these evaluation functions that we'll use when we're kind of getting lower in the tree. We can't go any lower. What would you use? Let's look at chess. What does it mean to evaluate a board situation and give a score for it? Well, typically what's done is to say there's a lot of things that matter. And you define a feature function for everything that you think that matters. So your evaluation function, something that looks like this. F1 is your first feature, and it could compute the difference between the number of queens that each player has. Feature 2 could be the difference between the number of knights. Feature 3 could be some number that you found in a chess book reflects how good a board situation you're in, kind of how well you're in the defensive situation, how well you're attacking the other guy's king, and so forth. So you have a number for all the things that you think that matter. You put them all into their own feature function, F1 through N. Now, you can only have one number in the end, so you have to sum them together. Now, you don't just sum them together because maybe one is more important than the other, so you put some weights in front of them. So this one has a weight W1, weight W2, up to weight Wn. Then you play with those weights. You say, oh, I think this one's more important, this one's more important, and so forth. That's your evaluation function. If you don't like tweaking the weights yourself, you could do things like playing it against itself. You could pitch your chess player against itself with a certain choice of weights, and then you could do hill climbing, right? Let's fix the opponent. You have a fixed opponent with some set of weights. That's your adversary. You have your own chess player you're trying to make as good as possible. You have some set of weights. You play, you see how often you win. You tweak the weights a little bit, right? You evaluate again. Is it better? You keep the change. Is it worse? Then you discard that change, right? So that's just standard hill climbing, standard kind of simulated annealing type procedure that you can run to automatically find the weights by repeatedly playing the game. Okay, so that's how it works. How about for Pacman? That's going to matter for you. Now, it's really important when you assign these feature functions and the weights for them is that you look at the numbers that come out. You need to look at board situations, and you need to make sure that when you compute your evaluation function for a board situation, that if the situation is better according to you, the evaluation function also gives a higher score. That's the way you can go about debugging your evaluation function. So let's look at some situations here. This is the reference situation here. How about this? It's kind of okay for Pacman, I guess. Not the best, not the worst. How about this? Well, it seems worse, right? So you'd want your evaluation function to be giving you a lower score for this because the ghosts are much more on Pacman's tail. How about this? Well, about the same as before, but you've already eaten some dots, so that's good. So maybe it's a little better, but still the ghosts are right with you, so it's not great. How about this? That better gets a much worse score, right? How about this? Potentially even worse. And now you're laughing, but the thing is, if you are designing that evaluation function, that's really what you need to look at. You need to look at a bunch of example scenarios and see if indeed your function will give better scores to the better situations. Yes? Is there something like admissibility and consistency? A good question. There is no such concept here in these Minimax searches. You just try to be as accurate as possible. There are guarantees if you are up to a certain accuracy, if you can guarantee that, but that's really hard to do because you have to verify by searching the entire tree. If you could guarantee a certain accuracy for your evaluation function, you can also guarantee a certain accuracy at the top as a consequence. But the more accurate, the better. That's just the way it works. It's not about being optimistic or pessimistic here. Okay, so let's take a look at what this looks like if you have Mastermind Ghosts who are playing Minimax with a good evaluation function against Pacman. Okay, here's the game. So far, so good for Pacman. Boom, done. What happened here? Initially, the ghosts are using an evaluation function because the game is still too far away from the end of the game to be able to search all the way. That evaluation function is guiding them towards Pacman because it's saying getting closer to Pacman is better. And when it gets close to the end here, somewhere over here, let's see. So right after here is when they decide that because the search is fast enough, they can look far enough ahead. And so they're not just both moving based on the evaluation function as close as possible to Pacman, but they realize that you should be flanking. They know that they can corner Pacman and that they will win the game by doing this. And so at this point, they just kind of finish up the game. Okay, so that's again cooperative behavior for two minimizer agents here. Now let's look at something really subtle about these limited depth searches. Depth 3 search is going on underneath here. And this keeps going. This will keep going forever if you have the patience. So what's going on here? Pacman starving is not eating the food pellet because it's not looking far enough ahead. Something very subtle is going on. So let's look at a very similar situation here on the slide. Pacman has two options. Another option there we're willing to consider. And then two options there. This is our game tree we're looking at, depth 2. Let's look at the evaluation here. This one, Pacman has made 2 moves, not eating anything, so that's 8. Here it has made 2 moves, not eating anything. That's 8. Wait, it ate something here. It's better than 8. It's 18. Not eating anything, 8. Here, 2 moves, 8 something, 18. So if 18 and 18, this is 18, this is 18, this is 18. Once you're at the top, you don't realize what's better. For depth 2, they're both equally good. It doesn't distinguish between when you would be eating that pellet. You'll be eating it after 2 steps. Either way is fine. Happens to break ties in this direction. Say it did that. You're now in a symmetric situation to the one at the top, right? These 2 situations are perfectly symmetric. Pacman is sitting in one of the 2 middle squares, just the other one. You can imagine the same depth 2 search tree process happening now. Again, it breaks ties the wrong way, and it turns around. And it keeps turning around and around and around. What's going on here? Something's wrong. What's going wrong is that because of this replanning, right, the way we replan, it doesn't execute that plan all the way, right? The initial plan here to go there was pretty good, was reasonable, if you had executed it all the way, but it doesn't. Since we do these replanning agents, that's always going to happen. It's not going to realize what it planned the previous time. What's another solution here? Well, it's to have a better evaluation function. We just used the utility function here. What if we say, well, sure, utility is a good approximation, but over here, you're already closer to the remaining dot, so let's do +1. Then you would have had 19 here, 19 here, would have gone this way, and everything would have worked out. So if you see this kind of thrashing behavior in your project 2, likely the bug is in your choice of evaluation function. It's not going to be the minimax, not going to be the alpha beta, it's going to be your evaluation function that is just not distinguishing certain states well enough. Yes? That's another way to do it. You could say, I'm planning this many steps ahead, I execute, and then only replan. Often that is not as good as fixing your evaluation function. Because replanning helps you to adapt to the new situation, whereas that wouldn't adapt to the new situation. This is, of course, there's only one agent, so you don't really have to adapt, but this is pictorially. You can imagine the same thing happens when ghosts are running around in other places. Okay, so let's take a look at what happens when you run the same search we had before, but with a better evaluation function. Remember, here's where it went wrong the previous time. Now it doesn't go wrong because the evaluation function is better. It accounts for being closer to the remaining dot. And there you go. Okay, so we've seen Minimax. We've seen what it can model. We've seen how to not, if you have to go all the way to the bottom of the tree. What we're going to look at now is something else. Evaluation functions make approximations. And that allows you to compute solutions, but they're approximate. What we're going to look at now is a way to decide that a certain part of the tree just doesn't matter. It's not affecting your solution. You can skip it. Okay, here's our Minimax example. You work your way down. You have 3, 12, 8, and you end up with a, I'll start here, 3. You have 3. You have to look at the next one to know what the value is. It happens to be 12, which is worse, 8, which is worse, so you keep your 3. There's no way you could have skipped the 12 and the 8, because until you know they're 12 and 8, you don't know that they're going to be worse than 3. So you couldn't know ahead of time what's here, so you have to look at them to know that the value here is 3. Once you've looked at all of them, you can pass it up. And here, 2. To know the value here, we had to continue to get 4, 6 there, so we know it's 2. We can pass that back up, and 3 will get retained, and work our way down here to know the value here. We have to, again, look at all of them to realize this is 2, and then at the end, we know it's 3 up there. Now, let's look at this again from a slightly different perspective, and not try to compute the values everywhere, but just the values we really need to know. We start the same. What we really want to know is the value over here. Keep that in mind. You know the value over there? Well, we start looking over here. 3, 12. We still don't know the other values, so we need to look at it. 3 is what we have here. So that's what we pass up. At this point, we'll go to the next one. We see 2 here. What does that 2 tell us? That 2 tells us that the value here will be less than or equal to 2. Now, no matter what's sitting over here, if this is less than or equal to 2, we know that it doesn't matter what's over here. 3 is always going to be preferable for the maximizer. So we don't even look here. We just pass up that this will be less than or equal to 2. That's it. Looking at the next one, 14. We know that this will be less than or equal to 14. Can we stop here? No, because 14 is better than 3, and so we don't know yet, because it could be something less than 14. We don't know what the maximizer would do. 5, so now we know it's less than or equal to 5 up here. Well, that's still higher than 3, so we don't know yet what the maximizer will decide just on this knowledge. Look at the last one. Now we actually know it's 2. We can pass the 2 up. The maximizer here will stick with the 3, and we never looked at this over here. So what we see here is that once you explored one option completely for the maximizer, you know that first branch of the tree gives me a 3. You can start using that when going down other branches to help you decide what's just useless to look at. Okay, when does this happen? This is probably the hardest concept of this lecture, alpha-beta pruning. When is it possible to just discard a part of the tree? Let's look at this example here. You're working on your minimizer node n. You're in your depth first search. Minimizer node n is being considered. You're looking at these children. You looked at a child, and you have some estimate of the value here based on the first child. Let's say you get some number here. We call it v. What that means is that this node will get something that's less than or equal to v once it's looked at all its children. Now, what we just were looking at in the previous slide for an example is that if there's a maximizer node above here, that maximizer has another option, and that other option is known to be higher than v, then the maximizer will never let you go to that minimizer node we're looking at now, because that's going to be lower than v, which is just too low. So that's what we looked at on the previous slide. Now, the subtle thing is that that maximizer node doesn't need to sit right here. It could be anywhere earlier on if over here the maximizer had a guarantee of A. So it fully explored an option. It knows it could get A there. Then if this minimizer node is considering V, and everything else going to just result in smaller than or equal to V, if it's the case that A is bigger than V, then the maximizer will not let things go down this path all the way here. It will never let that happen, because that will result in a worse result than going this way. Since you know it will never happen that you will follow this path in the game tree, you know that you don't need to continue evaluating this node, because you'll never go down all that path down to that node. You can stop evaluating it and just pass up that this will be less than or equal to V. That's alpha-beta pruning. It means you get to prune everything else here. And that could be a very big tree. This doesn't have to be just a bunch of values. It could be a subtree underneath each of these that's another 100 deep. You completely get rid of that. Yes? Say it again? It's the same, but the extra thing to keep in mind is that the maximizer doesn't need to sit right above. So here the maximizer was sitting right here, had an option here. We're looking at this minimizer node. Here the maximizer is sitting up here, again here, but is also up here. And the better option A is available over here. So not just one level above, but anywhere higher up. If you've seen an option that's better than what you're going to get down here, you don't have to even consider what's down here. So it's never going to be happening. So this is exact, because you know this will never happen. The game will never end up over here. You can ignore it and get rid of a big part of your search tree without losing accuracy. Here's something similar for max. This is what it looks like. Code-wise, very simple, right? Coding this up, it's very simple, but really wrapping your head around what's going on is a lot harder. It's just an extra line of code here. You keep track, let's look at the minimize, which we have been doing, of two extra variables, alpha and beta. Alpha is the best thing the maximizer has seen so far somewhere higher up in the tree, and beta is the best thing the minimizer has seen. You keep track of both of those. You still initialize your value as plus infinity. You loop over your children, compute the value of your children, and you update your value accordingly. Then you check. If the value you currently have is smaller than alpha, this is for the minimizer, you find a value smaller than what the maximizer could have guaranteed by going somewhere else, then you can stop. You know the game's not going to come down here in this part of the game tree. You can just return that value v. If not, you keep going. Now, while you do this, you have to do some bookkeeping, because you're always passing down recursively the best option higher up on the path to the root. So you have to keep track of that best option. And so the best option so far was beta. If the new value is lower than beta, well, then the new value is a better option than beta. You need to update. So the code's very simple, but the concept's pretty hard. So what's important here? No effect on the values you compute at the root node. So the value you get up here will always be the same, whether you run alpha, beta, pruning, or minimax. But for other nodes, you might get different values. Why? Because you stop evaluating at some point, you already passed something up. And that's not the right value. That's not the minimax value. It's going to be less than or equal this kind of thing. But we get the right thing at the root. Now let's see what could go wrong in your implementation in project 2 in your alpha beta pruning. You're running this alpha beta pruning. What do you get here? 10, right? That means now you have an option for 10. You work your way down here. The first thing you see is 10. This means this will be less than or equal to 10. Well, less than or equal to 10, I already have an option of 10. I don't need to consider this anymore, because it's going to be less than or equal to 10. So I pass up 10. Now we have a 10 up here. But the problem is that you get that 10 on top, but you don't know which one of the two is the right one to go to, left or right. They both have a value of 10. The one on the left is actually the minimax value, but for the one on the right is this alpha beta thing that was computed, right? And it's not the right value. So what are you going to do to solve this? Well, we know we have a guarantee that at the top it always works out. So one solution is to say, I'm not running alpha beta pruning from the top, but I'm looking at all my children, and I'm running, if I have 5 children, I'm running alpha beta pruning 5 times. Once for each of the children. That gives me the exact values for each of the children. And then at the top, I can decide which of my children, of these 5 children, is the best one. That's the maximally effective way of doing this. An alternative way of doing this is to not prune because of smaller than or equal, but instead only prune when something is strictly smaller. That'll also solve your issue, but you'll get less pruning, so it'll be a little less efficient. Okay. If you're lucky, and you have the perfect ordering of your nodes, remember, when you go down your search tree, you have a choice, go left first, right first, and so forth, right? If you do the perfect thing, and what that actually means is picking the most promising ones first. For the minimizer, things that look really bad, right? Really low scores. For the maximizer, things that look like they'll have really high scores. If you do that, and you do that correctly, you'll get maximal pruning. Of course, you don't know how to do that, but you can use your evaluation function to guide you what will be very good for the minimizer, what's very good for the maximizer, and so first go where it's best for the current player. That'll optimize the amount of pruning you get. If you have the perfect ordering, you will prune effectively, very effectively, and you'll have an effective branching factor that's a square root of the original branching factor. What that means is that now you have a running time order b to the m over 2. That means you run a lot faster, or if you have a search depth limit, it means that you can effectively search twice as deep. So alpha beta pruning with the perfect ordering will allow you to search twice as deep with the same running time as it would take Minimax to search only half that depth. So it's a very big difference that it can make. But if you don't get the ordering right, of course, then you might still do just as much work as Minimax. Okay, what this is here is the first time we've seen something that's called meta-reasoning. And alpha-beta pruning is this additional piece of computation that we put into our algorithm that tells us whether it's worth to do a certain computation or not. All right, that's it for today. Next time we'll see how to deal with stochasticity.